This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
Modern power grids are built on a foundation of inefficient thermal emitters and unstable terahertz sources. These systems are structurally incapable of meeting the precision demands of next-generation defense and industrial sectors. Closing this gap requires a specific technological benchmark, a scalable, high-Q quantum infrared source stabilized at exactly 114 terahertz. The Kozloduy Harmonic Mode Reactor, or KHMR, is engineered to meet this requirement. It functions as a non-equilibrium quantum optical engine, utilizing a double resonant cavity to translate input pump energy into a coherent mid-infrared output. This architecture operates as a harmonic amplifier of vacuum fluctuations. By stabilizing these modes within strict thermodynamic limits, the KHMR generates a measurable, extractable energy flux, establishing a high-efficiency alternative to traditional combustion and nuclear fission. The reactor core utilizes a Chi-2 double resonant cavity. This design ensures that the pump mode and the signal mode are simultaneously resonant, which is the primary mechanism for achieving an ultra-low oscillation threshold. This diagram shows the scaling laws governing that threshold. Note the nonlinear coefficient, or D effective, in the denominator. Because this value is squared, increasing the material's nonlinearity is the most effective way to force the threshold power to drop. This is why we rejected lithium niobate in favor of orientation-patterned gallium arsenide. Gallium arsenide offers a nonlinear coefficient of 94 picometers per volt, roughly 3.5 times stronger than lithium niobate, paired with 11 times the thermal conductivity. By integrating this specific material with precise quasi-phase matching, we reach a state of near-zero effective phase mismatch. This transforms the KHMR from a theoretical concept into a verified engineering reality. Because the system operates at such high Q factors, it is extremely sensitive to thermal noise. Maintaining resonance requires a stability window of just plus or minus 20 millikelvins. This Micro-Kelvin level requirement is why the pilot deployment is staged inside the empty reactor chamber at the Kozloduy nuclear power plant. A decommissioned nuclear chamber provides the exact defensive properties the core needs: enormous Faraday shielding to block electromagnetic interference, and nuclear-grade vibration isolation. This industrial environment creates a stability moat for the reactor. It protects the quantum harmonic frequency from macro-environmental disruptions, ensuring the coherence of the 114.11 terahertz signal remains unbroken. With a stable optical output established, the next engineering challenge is converting that high-frequency field into grid-ready 50 Hz power. This diagram illustrates the function of the optical rectenna. A nano-antenna captures the terahertz wave, while an ultra-fast tunnel diode rectifies the signal into a stable direct current at frequencies where traditional electronics fail. That DC signal is then processed by a PCS 6000 inverter. This system filters harmonics to lock the output to 50 Hz, with a frequency accuracy of plus or minus 0.005%. This direct conversion chain allows the KHMR to function as a complete photonic electrical reactor. It bypasses the losses of traditional thermal cycles, targeting a theoretical maximum efficiency of 75%. For defense applications, this efficiency translates into tactical autonomy. The KHMR is designed for black start microgrids, providing up to 3 megawatts of power to isolated installations without any reliance on an external grid. Each module is built within a sub-20 square meter footprint with EMP-protected circuits. This allows for rapid deployment via strategic heavy airlift to any global theater. Operationally, the unit is nearly invisible. It produces zero detectable emissions and uses post-quantum cryptography to secure its SCADA telemetry uplink. By eliminating the logistical tail and fuel lines required by traditional generators, the KHMR enables long-duration deployments with a drastically reduced thermal and acoustic signature. The deployment roadmap is already in motion. We are currently entering a 3 to 6 month proof of mode phase at the Bulgarian Academy of Sciences to verify the core cavity inserts. Following this validation, the Phase 2 Kozloduy pilot will lead to the TerraGrid Omega, a nationally synchronized network of 12 clusters capable of delivering 1.72 gigawatts of power. Because the KHMR uses no nuclear fuel and produces zero radioactive waste, it carries a zero-input regulatory classification. This allows the project to bypass the years of traditional atomic oversight and move directly into the €400 billion energy market. To complete the Phase 1 de-risking and move toward the Phase 2 pilot, we are opening a €2.5 million seed round today. The physics are established and the industrial infrastructure is secured. The opportunity for institutional investors to enter this €70 million annual revenue pathway is now.